Okay, in this video we're going to talk about molecular, total ionic, and net ionic chemical equations. Now, molecular equations are basically just the type of equations that you've already been using. So anytime that you write a normal chemical equation, you complete it and you balance it, that's also called a molecular form of the chemical equation. So we're going to expand that basic molecular form of the chemical equation, and we're now going to write two more forms of a chemical equation, the total ionic and the net ionic forms. So to do this, we're going to first write a molecular equation for a chemical reaction in the molecular format here. And then I'll show you how to expand that into the total ionic format. And then from the total ionic format of that equation, we can get the final net ionic format of the equation. So the example we're going to use here is for the reaction of lead-2 nitrate reacting with potassium iodide. We're going to assume a double replacement reaction and write the correct state indicators, which means we're going to have to use our solubility rules for this. So I've got my solubility rules table, and I'll be referring to that here in a moment. Okay, so we're going to write this equation. Lead-2 nitrate. If it's a lead-2, that means there's a +2 charge on the lead. Nitrate in O3 has a -1 charge on it, so I have to have 2 of these nitrates to balance out with the lead-2. Reacting with potassium iodide. Potassium has a +1 charge. Iodide has a -1 charge, so I need 1 of each. And they're going to react in a double replacement reaction. Now, it wasn't explicitly stated, but we can assume that these are in aqueous solutions. They are both soluble. So basically, we are going to add an aqueous solution of lead-2 nitrate to an aqueous solution of potassium iodide. Double replacement reactions, the cations are going to switch places. So I'm going to get the lead-2 cation, and that goes with the iodide. And since iodide has a -1, I'm going to need 2 of them, 2 of those iodides to balance with that lead-2 cation. And now the potassium is going to go with the nitrate. And they're +1 and -1, so I only need 1 of each. Notice that although there were parentheses around this nitrate, there are no parentheses around this nitrate. Why is that? Well, because in this case, we had 2 nitrates, and so I needed the parentheses with a subscript 2. But to charge balance over here with the +1 potassium, I only needed 1 nitrate. So it would be incorrect to put the parentheses here, since there's only 1 of those polyatomic ions needed. So those are the correct formulas for my products. I'm now going to determine their solubility. So lead-2 iodide. If I look at my solubility rules, I see that rule 1 does not help, rule 2 does not help, but rule 3 talks about iodide ions. It's in the generally soluble column. So generally, iodide compounds are going to be soluble. But there's an exception here for the lead-2 salts. So this lead-2 salt is not soluble. It's insoluble. And so it's going to precipitate out as a solid. For potassium nitrate, group 1A ion, right there in rule 1, it's going to be a soluble salt. And so it gets an AQ here. So I have the correct state indicators. The next step is I have to balance my equation. So here I go, 1 lead, 1 lead. 2 nitrates, 1 nitrate. So I need a 2 here for 2 nitrates. Starting back at the beginning, 1 lead, 1 lead, 2 nitrates, 2 nitrates, 1 potassium, 2 potassiums. Fix the potassiums. I changed something, so I start over. 1 lead, 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 2 iodides, 2 iodides. And it's balanced. Okay, so now that I have the completed and balanced chemical equation with the state indicators, this is what is also called the molecular format of a chemical equation. So, if I go back up here to my instructions, it says, then write the total ionic equation for the reaction. And to do this, everything that is aqueous must be broken into its actual ions, since that is how they actually exist. So, in a previous video, we talked about beaker diagrams or particulate diagrams and how we represent aqueous or dissolved compounds as dissociated ions, because that's how they actually exist in solution. So the whole point of a total ionic equation is to represent these species as dissociated ions in solution if that's how they exist. So basically, if it's going to be aqueous, then we're going to break it apart into its individual ions. The exception to that is unless it is a weak acid, because weak acids by definition do not dissociate completely. So the general rule is if it's aqueous in the molecular format, then we're going to break it apart into its dissociated ions, except for weak acids. Weak acids are aqueous, but we're not going to dissociate them. So here we go. If this species is aqueous, it is, then we're going to represent it down here as dissociated into ions. So I've got a single lead-2 ion right here. So I've got to write a lead-2 ion right there. Notice now that because the ions are alone by themselves, we absolutely have to have their charges explicitly shown. So I've got a single lead-2 ion, and it's now dissociated. So I bring it down as dissociated. And I give it its own state indicator because it is now a species alone by itself. So every species gets a state indicator. This is dissolved in water, it's aqueous. Next. I do not have a single species that is an NO3 parentheses subscript 2. What I have here is 2 nitrate ions. So the same way that I wrote them using my coefficients when I was doing particulate or beaker diagrams, that's exactly the same way I'm going to represent them here. I have 2 nitrates, and here's a nitrate. Notice the coefficient here takes the place of what that subscript was telling me, that I had 2 nitrates in that formula. Once they're all dissociated, now I have 2 nitrates that are now dissociated in solution, and they are aqueous. And so I have broken that compound up into its constituent ions. Over here, we move on. This is an aqueous compound, so it's going to be broken apart as well. Notice I have now 2 of these potassium ions. 2 potassium ions that are aqueous. And I have 2 iodides. Must have the charge, must have the state indicator. So now everything on the reagent side that was aqueous has been broken apart, dissociated into its individual ions. Moving on, I'm going to start with the product side. I might run out of room, but I can put a little bit down here. That's okay. So on the product side, this is lead-2 iodide. Notice it is not aqueous. If it's not aqueous, that means it is not dissolved in water. That means it is not dissociated into individual ions. So I am not going to dissociate it down here. If it's a solid, liquid, or gas up here, I'm going to bring it down as is. So I've got a lead 2 iodide species. I did not break it apart because it is not aqueous. Moving on, I have 2 potassiums that are aqueous. And sure enough, I'm going to run out a little space, so I'll just put these 2 nitrates. Because there are 2 nitrates represented right there, and they are aqueous. So notice here, when I had subscripts that referred to how many of these species I had in a compound, I used my coefficients to represent that down here. When I had a coefficient that represented more than one of these species, I also had to bring the coefficient down to represent that I had more than one of these ions. Oops, I need 2 nitrates, don't I? 2 nitrates. So 2 nitrates, there we go. Almost made a mistake there. Okay. So now I have my total ionic format of the equation. Total ionic format, all it means is that everything that is a dissociated ion in reality is written that way, as a dissociated ion. And if it's not a dissociated ion, then I do not break it apart. Okay? So if in my molecular format of my equation I have something with an S or an L or a G, I am not going to break it apart. This includes water. Water is a liquid, not an aqueous compound. So if water, liquid water, were up here, I would not break apart water. Okay, it would just come down as H2O liquid. All right, last step. It says, then write the net ionic equation for the reaction. And to do this, we cross out anything that appears identical on both sides of the equation. So if it's on one side of the equation in one form, and it appears on the other side of the equation in exactly the same form, that means it did not change. If it's over here and it's over here on the product side, then it means nothing happened to it. Such ions do not participate in the reaction and are therefore called spectators. Like the spectators of a football game, like the spectators of a basketball game. They don't participate in the game, hopefully. So we call them spectators because they're just watching. And whatever is left after I've crossed out the spectators is what actually reacted. So here we go. I'm going to cross out the spectator ions. So I look for anything on the reagent side that is identical to the product side. Can you spot anything? So the lead 2 plus does not appear over here. The 2 nitrate ions, yes, they do appear on both sides. So evidently nothing happened with them. They were there on the reagent side, they're there on the product side, they did not react. So I'm crossing them out. They're spectator ions. Anything else? It looks like these 2 potassium ions are spectators as well. Anything else? I don't see anything else that is in exactly the same form on the reagent side as it is on the product side. So now we have crossed out all of our spectator ions, and then whatever is left is what actually reacted, and that's what we're going to write in the net ionic format. The word net literally means whatever is left over after you've added or taken some things away. So for example, if you get a paycheck and you have your total pay, what's called the gross pay of your paycheck, and then they subtract amounts from the paycheck due to taxes and so forth, and whatever is left is your net pay. So net ionic format is literally the ionic format that is left over after we've crossed out some things. So everything that is still uncrossed, everything that still exists up here that I haven't crossed out yet is going to be brought down here and written. So the lead 2 plus ion comes down. What else? The 2 iodide ions. That comes down. What else? The lead 2 iodide product comes down. And there we go. There's my net ionic format of the equation. So there are a couple of points I'd like to make about this net ionic format of the equation. Once you have done this, you now have the species that actually reacted in this reaction. When I added the potassium iodide and the lead 2 nitrate solutions together, the potassiums and the nitrates did absolutely nothing. But in this reaction, a single lead 2 ion encountered 2 iodide ions, and when they collided with each other, they formed an insoluble compound that then was no longer dissociated and therefore began to turn into a solid and would eventually precipitate out of the solution and settle to the bottom of the beaker or test tube. So this is what actually reacted. We have our spectator ions that are still floating around in solution. So yes, they are still there. They just didn't participate in the chemical reaction. I'd like to point out also that it's absolutely critical that we have our formulas for our products written correctly, because if we have the formulas for the products incorrect, then we won't be able to balance the reaction, and then these amounts, these coefficient amounts, will all be incorrect. And another thing is, if we got these state indicators incorrect, then that would have caused us to dissociate species when we shouldn't have, which means we would have ended up crossing them out as spectators when they're not really spectators. So this type of a problem, writing net ionic equations, requires us to bring together a lot of information, a lot of competence that we've developed in predicting products, in writing their correct formulas, in using the solubility tables to determine their solubility, in balancing a chemical reaction. All of those skills come together to allow us to be able to do this. Now, why is this important? Well, it's important to be able to write net ionic equations because it's the net ionic equation that tells you what the chemical reaction actually is that's taking place. And here's something else. There are a few different ways that your net ionic format can turn out. It could be that maybe you have nothing that is a spectator ion up here, which means nothing is crossed out, and therefore everything in the total ionic format is rewritten down here, which means that everything reacted. Or you could have a situation like we had here, where some things are crossed out and others are not, which gives a situation like this, where your net ionic format shows that only some of the species reacted. Or, and this is especially important, you could have a situation where your products are all aqueous, and if they're all aqueous, then they are all dissociated into ions unless one of them is a weak acid. And if they're all dissociated as ions on the product side, then you would have everything crossed out, and there would be nothing left over to bring down to this last stage. And when that happens, that tells you that you get no reaction, because there's no net ionic format left over after you've crossed out the spectators. So let me repeat that. We have three different possibilities. We'd have a possibility where everything reacts, where some things react, and where nothing reacts. And what tells us which of those situations is going to occur is going through this process and finding out what is written at this net ionic format stage. So with that said, remember that when you have a single replacement reaction, that's not what this is. When you have a single replacement reaction, what tells you whether the reaction is going to take place? It's the activity series. When you have a double replacement reaction, what tells you if a reaction is going to take place? It's the net ionic equation. So that's what this statement is reiterating down here. Notice that for a reaction to actually occur, there has to be something left over that is then brought down into the net ionic equation. Otherwise, everything is just a spectator and it's crossed out. So if no reaction takes place because you have nothing left to bring down, we just write NR for no reaction down here for the net ionic reaction. And that's how we work from the molecular format of an equation to the total ionic format of an equation to the net ionic format of the equation. In the next video, we'll do a couple of sample problems so you can practice this skill.